Children, are you to? Is this being patched to YouTube? Yeah. Okay. So let's start then. Today we'll be briefly going through some of the properties of Legendre symbols. Then, following that, we'll be looking at the theorem of quadratic reciprocity. And finally, we'll be, if we have time, we'll go through Jacobi symbols, which are a kind of generalization of Legendre symbols to all numbers instead of prime numbers. So, the first thing, yeah, exactly, Ashir. So, the first thing that we are doing is we look at a few properties of Legendre symbols. First, some but the first one is A by B is equal to B by B if A is congruent to B mod. If A congruent to B mod. So I hope this is directly visible, because if A is congruent to B, then if you have something satisfying x square congruent to A mod B, then you also have, like, the same number will satisfy the equation x square congruent to B mod. Right, so this is just direct. One of the more useful ones is the following, which is A B over B is equal to A over B times B over B. And this is a direct result of for A, for, yeah, A and B have to be co-prime with B, but yeah. In fact, if we just, so A and B do not have to be co-prime with each other, but they have to be co-prime with B. Like, that's basically when the Legendre symbol is defined also. There is a variation of the Legendre symbol which simply assigns 0 in case B divides the number. So A by B is 0 if B divides the number, and for that variation, in fact, this will be true for all A and B. The proof for this is pretty simple. We have already shown that well, x over b is equal to, or rather congruent to, sorry, congruent to x raised to b minus 1 by 2. Correct? So just AB over B will be equal to AB raised to B. Yeah. So via Euler's criterion, exactly, AB over B will be equal to AB raised to B raised to B raised to B minus 1 by 2, which can then be broken up into A raised to B minus 1 by 2 into B raised to B minus 1 by 2, which then gets congruent to this. right? Because these are numbers which are just +1 and -1, no? Both the left hand side and the right hand side have to be strictly equal to +-1. So if they are congruent, then since by definition the Legendre symbol numbers are restricted to be equal to +-1, this has to be true, correct? Right. So we were just discussing a few properties of Legendre symbols. The first one being the simple: if A congruent to B mod B, then A by B is equal to B by B. The second one, a little bit more involved, is that AB by B is equal to A by B into B by B. And this can be easily proved by taking a detour using the Euler's criterion. That is, if x by b, the Euler's criterion states that x by b is congruent to x raised to p minus 1 by 2 mod b. Right, so AB by B is congruent to AB raised to B minus 1 by 2, which is congruent to A raised to B minus 1 by 2 into B raised to B minus 1 by 2, which is congruent to this, the value on the right. And since both the values by definition of the Legendre symbol are constrained to be equal to +-1, the congruence can be directly written as an equality. So if everyone's fine with this, right, we'll go to the next. The next two properties would be the values of specific values of the Legendre symbol, which we'll use in a while, which become pretty useful actually for computing any general value along with the multiplicity theorem. The first question we'll be asking is, what is this equal to? Or equivalently, what criterion of B will give us this equal to 1? So, yeah. So for what values of B would -1 raised to B be equal, -1 upon B be equal to 1? So just by using the Euler's criterion, this is equal to -1 raised to B minus 1 by 2. Yeah. So just -1 equal to, and so the answer directly pops out is that this is true if B is congruent to 1 mod 4. Right? So this is pretty direct, and I hope everyone's fine with this. Then we look at one more value and leave it. Well, just for just for fun, what would this be equal to? Yeah, this will always be equal to 1, because 1 is the square of 1 at the very least. So there definitely exists 1 square. And if you remember our Euler's criterion, this also means that B, in general, you can also see that B minus 1 whole square would also be 1. So 1 by B is always 1. Just continuing here, the next most natural question would be, what is the value of 2 by B? The reason I'm asking this specifically is that, as you'll see in the future, quadratic reciprocity will actually tell us a way to compute something like P1 over P2 for all odd primes. So, in fact, what will be left over would be the case where there is a like the case of 2 basically. So again, once you factorize, you'll have a lot of odd primes which can be which can be found out using a few steps using the reciprocity theorem, and then you'll have a power of 2. Generally, if it's 4 or 8, then you can write it as 2 raised to some 2k and then into 2, and what you'll finally be left with would be a single 2 over k, if that makes sense. Right, so that leads us to the question of what is the value of this factorization. So, okay, Arjun, I'll give you an example. Just give me any. So, Arjun, what I mentioned just now is that we will look at how to find the values of P1 over P2 separately, and as we have seen, let's say 15 over P can always be written as 5 over P into 3 over P. So as long as you can, P1 and P2 are primes. So as long as you can factorize them into a set of odd primes, we will deal with it in a bit. But assuming that we know how to take care of odd primes, the only thing left is taking care of 2, if that makes sense. Right, so we come back to this question of how to find 2 over P. Does anybody have any intuition for this? Or does anybody know how to do this already? Right, Ashwin, and then what will be? Okay, so let's not we'll go about this in a little bit roundabout manner. Right, we'll go about this in a little bit roundabout manner. We'll first look at what Gauss's lemma tells us about this. So if you remember from our previous class, in fact, there are other primes for which this is true. Actually, 4k plus 3 is also not always correct. Let's look at how to approach this. A and B are not congruent. Sure, man. Just keep typing and then I'll respond. So A and B are not co-prime in the Legendre symbol case. What exactly are you referring to? Are you referring to this? If it is this, then yeah, A and B need not be co-prime. Right, so going back here, let's look at what Gauss's lemma tells us about this. If you look at this through the lens of Gauss's lemma, then it tells us that you have all the numbers, KB numbers from 1 to p by 2, like p minus 1 by 2. Then we take a look at what the value of 2k is. And if you remember our previous class, we divide this into two sets, L and M, where L is the set of all the numbers whose residues mod p are greater than p by 2, greater than p. And M is the set of all the numbers which are less than equal to p minus 1 by 2. And then we directly say that over p is equal to minus 1 raised to L. That is the size of it, right? So looking at the particular case of 2, since k varies from 1 to p minus 1 by 2, that means 2k varies from 1 to p minus 1. So we don't have to look at what happens when we take the residue mod p, because that will just the value of 2k itself. So the number of Simran, just tell me when it becomes okay. Simran. Tell me when it becomes okay so that we can continue. Sorry everyone, we're just facing a small technical difficulty. Till then, everyone in the SIQ class, please do mention if you have any doubts till where we reached. In fact, why don't you try to figure out how to reach from here to the solution? We've almost reached the end of the solution for over P. Okay, so I think it has become okay. So let's continue then. So as I mentioned here, since k lies between 1 and p minus 1 over 2, 2k will lie between 1 and p minus 1. So the question basically becomes how many even numbers there are between 1 and p minus 1 over 2. That should be equal to b over 4, right? Now, I hope this makes sense. So given this, then the mod of L, the size of the set L, be equal to b minus 1 over 2 minus b by 4. Right. Now we just take, we'll just see what b is congruent to. You can start with 2 and 4, and then finally you'll have to take b congruent to some values mod 8. So mod 8, if you see, b can be congruent to 1, 3, 5 or 7 mod 8, right? So again, mod 8, if b is congruent to 1 mod 8, then b minus 1, yeah, so b minus 1 over 2 would be a multiple of 4. So let's just write this as 4k minus b by 4 would again be 8k plus 8x, or rather let's just let me use some calculation. Let's call this 8k plus 1, 8k plus 2, 8k plus 8k plus 1, 8k plus 3, 8k plus 5, and 8k plus 7. So, so the issue becomes k plus 1, 3, 4, actually 4k plus 1 and 4k plus 3. Then let's actually consider it mod 4 first, so that we know why. So if you consider it to be either 4k plus 1, the reason we are doing this is because actually the number that we get over here, we need to see whether this number is odd or even. So 4k mod 4, you will get some values of model, but it will not be easy to see whether the value of mod L is odd or even. Why do we want the parity of model? Because finally, remember, we have to calculate minus 1 raised to model. So what we basically need is the parity of model. So just going to the just going to mod 4, if you consider 4k plus 1, 4k plus 3, then you will have a p minus 1 by 2 would always be 2k. Here it would be plus 1, and then plus mod p by 4. So that is, in this case it would be k, and in this case also it would be k. So basically our solution then depends on, oh sorry, yeah, this is minus here. Minus. So you basically get k here and k plus 1. So it becomes non-trivial to find whether this value is odd or even, correct? And finally, what we need is to find whether this value is odd or even. So instead, we just look at the residues mod 8. Arjun, I hope that is that you understood that. Yeah. So mod 8, then we do the same thing. We have p minus 1 by 2 would just be equal to 4k here. 8k plus 3 would be 4k plus 1. 8k plus 5 would be 8 plus 2 and 4k plus 3. And then have minus, we have p by 4, which is just 2k for all of these values. And 2k plus 1 here. And we'll find that this value is even in cases of this and this. That is when when the prime is congruent to 1 or 7 or 8. Is this fine? So p congruent to 1 or 8, 1 or 7 or 8. So an alternative way to write this would be, in both of these cases, p squared minus 1 over is congruent to, so p square minus 1 over 8 is congruent to 0 or more. Right? So p square would always be congruent to 1 or 8. Right? So these are the basic 4 properties that of Legendre symbols that we can consider. The first 2 were direct. If A is congruent to B, then A by B is equal to B by B, and that the Legendre symbol is multiplicative in nature. Then finally we have some values here. Minus 1 is square root on p if p is congruent to 1 mod 4, and 2 is a square root on p if p square minus 1 over 8 is congruent to 0 mod 2, or p is congruent to 1 or 7 mod 8. With that, we're finally ready to tackle what happens to the odd primes. That is, let's say 5 over 7 or 5 over 11 and so on. Right. And here we get an interesting concept. What people basically asked is whether there is a relation between the value of p over q and q over p. Right. So Arjun, what I was mentioning is we are done with the case when the value is actually 2, and just in case we get tricky questions such as what happens, what is minus 27 over p or something, we have also done with the case of minus 1. Remember, we can factorize the numbers, so all that is left is the case of case where there are where we are considering 1p over 1 prime over the other prime. So cases where both p and q, and we have to find p over q. And for this, well, people actually thought of a relation between this and Q over P. To make sense of this, what we are trying to do here is to find a relation between x square, between the existence of a solution for x square congruent to P mod Q and x square congruent to Q mod P. This is where the the meaning of the word reciprocity comes, because we're looking at two seeming reciprocals here, P by Q and Q by P, right? And in fact, a direct solution is available for the value of P by Q into Q by P. And this is equal to minus 1 raised to P minus 1 times Q minus 1. Looks eerily similar to the Euler's criterion, right? So basically, since it's minus 1 raised to the value, you just have to see whether it is odd or even, right? Because at the end of the day, that's all that matters. Whether P minus 1 over 2 and Q minus 1 over 2 are odd or even. Oh yeah, so it's this, or it's equal to minus 1 raised to P minus 1 over 2 into minus 1 raised to Q minus 1. My bad. Right? So yeah, let's go ahead and try to prove this. This is not a trivial proof in any way, and in fact we use lemma before we prove this. After proving the lemma, actually, yeah, so remember, Arjun, that x raised to, yeah, the reason why we cannot do what you're saying, Arjun, is so just to explain what Arjun is saying, he's saying that we'll use the Euler's criterion directly to replace P by Q with minus 1 raised to P minus 1 by 2. The reason why we cannot do this is because this replacement is true only mod Q. So actually, the first replacement would be correct mod Q and the second replacement would be correct mod P. But you cannot really do both of the replacements at the same time. Right? Does that make sense? Yeah. So then if we are unable to do this, let me just erase this. What do we do? And well, the idea then is that the only thing we know till now which doesn't really depend on mods, that is Gauss's lemma. If you remember, Gauss's lemma simply translates this to a number of something, right? So in fact, instead of looking directly at Gauss's lemma, we will look at another lemma, which basically says that if n is equal to summation j 1 to so Gauss's lemma can be quoted just because it has a name, but it's also a well-known lemma in the reciprocity theorem. So if you mention that you are using the Gauss's lemma for the Legendre symbol, then I think you can use it directly without an issue. Yeah, you won't have to prove it. Because, so generally, if it has a name which is, quite famous, then you won't have to prove it. If it can be referred to and looked up uniquely, then that should be enough for you to write. In this case, I don't think you'd have to. Let me actually get back to you about when you can exactly. So I'm not really sure about why it is an exception. I'll just talk to Anushka ma'am and maybe look up and find out why you would have to prove it if you have to prove it. I don't really know off the top of my head. So yeah, I'll come back to you about this in the next class. But I'm pretty sure that Gauss's lemma being as famous as it is, like as long as you mention that it is in the context of the Legendre symbol, it should be fine. So yeah, going back to this, instead of using, let me just find out why that is the case. But yeah, going back to this, instead of using Gauss's lemma directly, we will use another lemma which says that if n is equal to minus 1, yeah, and I'll check and come back. J A over B. This value of n, A over B is congruent to minus 1 raised to n. It's equal to actually minus 1 raised to n. And just to complete this, this would be true only if it does not divide A. Or rather, we will prove for the case when this is actually, so as far as I know, there were this was one of those cases where the original inventor of the quadratic reciprocity left no proofs. There were a couple of famous sort of proofs which did not pass muster. One was a wrong proof, and then one was a proof which depended on lemmas which were not proved. And yeah, it took a lot of time to actually reach this proof. So it's a very highly non-trivial proof that way. Exactly. So yeah, coming back to this, so for cases where it does not divide n, you have the lemma states that if you calculate this, then A over B is congruent to minus 1 raised to this value. And why is this true? Well, let's go back to Gauss's lemma. Gauss's lemma simply has values from a slight amount of lag here. A 2a and so on up to p minus 1 by 2a. Just did this before, but yeah, we have these values and then we look at its remainders and divide it into two sets, right? I mean, I think you pretty bored of this already, but yeah, we divide it into two sets, L and M, depending on whether it is greater than p by 2 or less than equal to p by 2, less than p by 2 basically. And then we take the mod of L. So let's just, for simplicity's sake, let's consider small n equal to mod of L. Right. Now we'll try to focus on this stage, the movement from the numbers to the remainders, because that is pretty non-trivial, and that's what doesn't allow us to simplify this lemma in any way, because while the sequence here is pretty direct, p minus 1 into a, the sequence after we get the remainders is pretty like random, and we cannot find any direct piece of the numbers we get after this step. So let's see what we're doing here. Let's say we have some value ja. Then what we can do here is write this as p times ja over p plus remainder, right? Just isn't this just equal to ja? Because if you have, let's say, this is plus remainder of ja mod p, so plus the value of ja mod p. Right? This is just a division theorem. We're dividing it by p, and this is the value of the uh, quotient, and this is the remainder left. Right? I hope this is clear. So what we can do is we can just sum this all up and write that sum of ja. Remember, we are just using the values from 1 to p minus 1 over 2. J minus 1 is equal to, we have the sum of all of these numbers, which is just n. So p times n plus the summation of li's and the summation of mi's. So it's supposed to be summation li plus summation mi. Again, if you have an issue with this, li mi are just the elements of the set L, capital L and capital M, which is visible here. This and this. No, so all of these remainders are divided into two sets here, right? So all these remainders are just the sum of all these remainders is equal to the sum of all elements in L and sum of all elements in M. So sum of all the remainders mod B just be equal to the sum of all elements in M and sum of all elements in L, right? So I hope this is, yeah. Now, if we write Mi and Li in terms of N, how can an element occur more than one time? We're looking at exactly these numbers here, right? We're looking at exactly these numbers here. We looked at them as JA, which is exactly what they were. Then we wrote that as P into JA by P plus remainder. And then we summed it all out. So the value here would be equal, the sum of all JAs would be equal to P times the sum of all of these was exactly what we denoted as capital N, if you remember, plus the sum of all of the remainders of these numbers mod B, which is exactly the values here, remainders of these numbers mod B, which is just all the elements in L and all the elements in M. So right, let me just write this as 1, 2, then the movement from here to here, this is 3, and the movement from all of the remainders to Mi plus Li would be written, would be 4, right? So, I mean, everybody should be clear with the movement from 1 to 2. Yeah. The 2 to 3 should also be fine. 3 to 4 is quite, so 1 is the same as this. Let me write this as sum of Ai, J for now, would be the sum of all of these elements, correct? So 2 is actually the sum of the remainders of all of these elements. And this step, let's call this xi for now. Xi are exactly the remainders here. And these remainders get distributed into two sets called L and M, depending on whether they are greater than p by 2 or less than p by 2. So the sum of all of the remainders should be equal to the sum of all of the elements in L. No, Li plus Mi is actually, so what we are doing here for Gauss's lemma, we take this tricky remainder here. If you remember what Gauss's lemma was, it was not directly dealing with this, but no, it's not the sum of all numbers from 1 to p minus 1. So it takes, for any a, it takes a to a, it will actually be the sum from 1 to p minus 1 over 2. That will also not be directly mod of Li plus mod of, okay, right. Let me just take an example. So let's take a equal to, let's say, 9 and b equal to 17. So, right, so the numbers here would be 9, 18 and so on up to 16 by 8 into 9. 9 is 72. So 9, 18 up to 72. Right? So what Gauss's lemma does is it takes the remainder of all of these mod 17. So you have 9, 18 would be 1, 27 would be 10, 36 would be 17 to the 34 plus 2 is 36, and so on up to 72, which is, let's say, 17 3 is a 51, 17 4 is a 68. So yeah, 4. So these are all the remainders of all of these numbers mod 17. You get that? Let me just actually write it all down. Right, so if this is fine with you, then what we further do is we divide these numbers into whether they are greater than 8, 8 being p minus 8.5 to be exact, or whether they are less than 8.5. And this gives us the L's and the M's. So right. So the other thing that we drew last class, if you remember, is that if you take all the numbers from, so the total number of elements here is p minus 1 by 2, correct? It does not span all of the numbers from 1 to p minus 1, right? There are 8 numbers here, and so after distributing also, like total elements in L plus total elements in M would always be 8. And we had proved, in fact, that if you take all the numbers p minus Li, and if you take all of the mi's, then this would be equivalent to a set from 1 to all the way up to p minus 1 by 2. Right? So the way we did this before, if you want to remember, is that we proved that none of the Li's are equal to one another. So all of the p minus Li's are distinct, all of the mi's are distinct, and then we had that section where we proved that p minus Li equal to mi gives a very weird result. So p minus Li equal to mi, then we can write this as we can also write this as p minus Li congruent to mi, and then we write this back in the terms of a, which is p minus something times a is equal to something else times a, and minus a I, let's say, congruent to a times I congruent to a times j, and then we get that I minus j is congruent to a mod b. Do you remember this? A times. And then this directly gives that p is congruent to a times I minus j, and since a is co-prime to p, we get p is congruent to I minus j, which doesn't make sense because both I and j are distinct numbers between 1 and p minus 1 by 2. Right? So we had this from the previous class. So how does this help us? This helps us in the following way. This So just adding all of the numbers here, you'd see that n minus summation of Li plus summation of Mi equal to 1 plus 2 up to p minus 1 by 2, which I can just write as summation j equal to 1 p minus 1 by 2 of j. This is just taking this, and so n is equal to mod m. L, if you remember, we have made this. N is equal to the number of elements in L. So just adding all the elements here and adding all the elements here, this should be pretty direct, that adding all of the elements here gives this, the RHS. Adding all the elements here will give n p's, that is how many ever elements of L there are, that many p's will be there, and then minus all of the elements of Li and plus all of the elements of Mi, correct? Just taking this term by term. This goes here, this goes here, and this goes here. Right, Darshan? I'm assuming that you might have a bit of trouble with one, but just remember that n is equal to the size of L. So let's say L has 3 elements. Then you'll have 3 p minus L1, p minus L2, p minus L3. So all of the 3 p's I plug together to write 3 into p. That's all that is happening. Right? So let me just plug this back in now. So we have this result, and remember we had this result before. I'm just going to subtract the two. So I'll write this in the opposite direction, that is this around, and subtract the two. So what you'll basically have is, you have summation ja minus summation of j, which you can write as a minus 1 times summation of j. Again, this might be a little bit difficult to follow, so let me write the left hand side of this as capital A, right? The right hand side of this is capital B. This is supposed to be B, but yeah, the left hand side of this is capital C, and the right hand side is capital D. So in that case, what I have done here is just C minus B is equal to D minus A. Equal to D minus A. Right? So A minus 1 times summation of J is equal to B times capital N minus small n. And then we have plus 2 mod Li. Plus 2 summation of Li, sorry. This is a little bit illegible, but what is happening here is B times capital N is here minus B times small n here, and then the mi's get cancelled out, and we have plus 2 times summation li's. Is this fine for everyone? This is a 2. Uh, Arjun, are you guys able to see the screen? Right, Arjun. So I'm basically subtracting this from this. Right. So the left hand side at least should be direct. It's just a minus 1 times summation of a j, which is just this value here, like this c value here minus this b value here. And on the right hand side, I have b times capital N minus b times small n, which I'm writing as b times capital N minus small n. Plus, I have an li here, and then I have a minus li here, so plus 2 times li. And then I have these mi's which get cancelled out, plus mi and plus mi. Arjun, are you able to see this? Are you finding this? Yeah. So everybody, I hope this equation is clear to you, because we have almost reached the end of this lemma. So now what we are doing is we'll just look at all of this congruent right. So just tell me what it is you need cleared up, then we can do that. Otherwise, if you have a doubt, please inform. We look at this whole equation mod 2. So remember I mentioned that a was odd, so a minus 1 is even, so this is congruent to 0 mod. And then you have b, which is obviously an odd number, so this will be 1 times n minus n, capital N minus small n, plus 2 times something, so that will be equal to 0 mod. Right? Which basically tells us that capital N is congruent to small n. Yeah, capital N is congruent to small n mod. Which means that minus 1 raised to capital N is the same as minus 1 raised to small n. Now we go back to our original lemma, which is just trying to prove that a by b is equal to minus 1 raised to small n. A by b is equal to minus 1 raised to small n, and shown that like Gauss's lemma already shows that it is equal to minus 1 raised to small n. So I mean we had to prove that this is equal to minus 1 raised to capital N. Gauss's lemma shows that it is equal to minus 1 raised to small n, so it has to be equal to minus 1 raised to capital N. Right? So, I mean, this is most of what was required for quadratic reciprocity. Let's just quickly go over it again so that everyone's clear. Technically, it's most of what is left. The rest is a little bit of really important equation, which which does take a leap of imagination, but mathematically it should not be that tough. So what we had to prove originally was that our lemma started with this: n is the summation from 1 to p minus 1 by 2 of this value ja upon p, which is just the sum of all of these numbers here. Yeah, sure. It is very tough to think of this, and given that's exactly the reason why there was a significant time gap between when the lemma of quadratic reciprocity, you can say, was actually provided as a theorem with the wrong proof, after which it took at least, I think, 4 to 5 years, and the tries of Euler gave a proof but had lemmas which were unproved, and then somebody else came and finally proved it. And then, yeah, and I'm not really sure. I can tell you I have it somewhere. Just give me a minute. Right, so it was first discovered by Euler, but Euler's first proof was false. It didn't properly it didn't pass verification. Later, Legendre gave a proof which unfortunately he had lemmas which he did not prove. So his proof was incomplete. And finally, Gauss independently discovered this law and presented the first complete proof. After which, the first proof obviously was very long, and it did take a lot of time for it to be simplified into this over and above that. But yeah, just let me just go through this proof again. The proof of this one lemma, we haven't proved the reciprocity theorem yet, but the proof of this, the lemma states that n is this number here, it's the summation from 1 to p minus 1 by 2 of all of, it's basically the sum of all of these numbers divided by the floor. So we'll take 9 divided by 17 and floor it, 18 by 17 and floor it, and so on. Generally, the proof is released. As far as I know, I'm not very technically sound about this, but generally we release the proof either through magazines or through lectures or something. And once it goes out to the public, independently mathematicians will verify it. And if it does not pass muster, if there is a logical fallacy, then somebody else will write about the fallacy. So yeah, the sum of all of the you take the sum of all of these number and you raise minus 1 to this to this number n, and the lemma was that this is equal to the Legendre symbol a over b if a is odd. How you do this is you depend on Gauss's lemma. You take all of the numbers in its full form. You sum it all up. The sum of these numbers can be written as we basically divide this using the remainder theorem. Using the divisibility theorem to b into j, b into a quotient plus remainder. The sum of these quotients, please note, gives us the value of capital N. So we can write the sum of all of these numbers as b into capital N plus the sum of all of the remainders, which Gauss's theorem, again, we are using a parallel to our proof of Gauss's theorem. Our proof of Gauss's theorem depended on two sets L and M, and they were basically sets of the remainders of these numbers. So when you sum the remainder of these numbers, then you'll get the same value as the sum of all of the elements of L and the sum of all of the elements of M. Then again, going back to Gauss's lemma, we see that while proving it, we showed that this set P minus Li for each element of L and all of the elements of M together, this set is a set of size b minus 1 by 2 and corresponds to the set of the numbers from 1 to p minus 1 by 2. And so just adding all of the elements in both of the sides gives you Pn minus summation of Li plus summation of Mi is equal to the summation of the numbers from 1 to p minus 1 over 2. we take this and we take the original equation that we got and subtract it from this to get this equation, which is just we take a common here, and a minus 1 times summation of j is equal to b times capital N minus small n plus 2 times summation of ln. Finally, we take this mod 2, so this disappears to 0, b changes to 1, and 2 times something disappears to 0, which basically becomes n congruent to small n, which means minus 1 raised to n is equal to minus 1 raised to small n. And hence, since Gauss's lemma already says that a by b is equal to minus 1 raised to small n, a by b is also equal to minus 1 raised to capital N. Right? Now, so what we have here is, so p by q is equal to minus 1 raised to summation let's see, summation of I'll leave that. Do you have a class right now? Okay, we have 15 minutes actually, so that's fine. Summation of j times p over q floor, right? And we have vice versa. Q by p is equal to minus 1 raised to summation of the floor of j q over p. Now, note that this again doesn't look remotely like the simple solution we had for the quadratic reciprocity, but at the very least we have factored this into a power of minus 1, which is not mod something, so we can just multiply these two. No, so here j is the summation value, which here moves from 1 to p q minus 1 by 2, and here it moves from 1 to p minus 1 by 2. So 1 to denominator minus 1 by 2, right? So I'll just write it down here, and then the other one you can fill up by q minus 1. This writing is really bad, but either way, going back, we at least have this in a direct form which can be multiplied without any issues, so to speak. So now let's try proving that this is actually equal to minus 1 raised to p minus 1 by 2 into minus 1 raised to q minus 1 by 2. For this, we will actually use a construction which will this. We are taking this. Now again, since the equation is since q and p are interchangeable, sure, I'll recommend some books, but also please, I'll recommend some books after this. But another equally useful playlist actually is Michael Penn's. If you look at the YouTube playlist of Michael Benz, especially for quadratic reciprocity. He has a separate playlist which explains the same proofs in a similar way. So you can definitely go through that too. Yeah, exactly. But as for books, MIs, yeah. So as for books, there are a couple that I prefer. There is, I'll send you a list later. But yeah, so to continue with the, yeah, everybody, I'll put it on the group. Right, so to finish this off, I'll just go with the assumption that P is greater than Q, since P and Q are interchangeable. And then we take a grid between, sorry, since this seems to be the bigger size, let's this is P and Q, right? And then we have sorry, this is a line between, this is a direct line between O and capital N. Yeah, I'll do that, or I can actually just ask Anushka ma'am for access and dump the PDFs there. So I'll do one of those. Don't worry. So yeah, let's just give names to all of these. No, these are not concurrent because, well, P is greater than Q, so this line will pass before the midpoint here, right? So just to give some names here, let's see, A, B. So the thing is, this is not the midpoint. This is not P by 2. I will just explain. It would be concurrent if this was P by 2 and this was Q by 2. But this is actually P minus 1 over 2. Remember, P by 2 and Q by 2 are not integers here either. So these are lines at P minus 1 by 2 and Q minus 1 by 2. Right. So with these, then let's call this A, B, C. Right here, we are looking at two different primes, so that obviously is not the case. Yeah, that's true. Correct. So now we look at different ways to find all of the lattice points contained in this rectangle OCBD. So actually, to make the maths simple, we look at all the lattice points which are within this, completely within this rectangle, as well as all of the lattice points on this line and all of the lattice points on this line. Because then, just by looking at the diagram, you can see that right? So we are looking at all of the lattice points within this. So we are actually taking a grid where all of the integers here are, you know, the grid lines here, and then the grid lines will join at, let's just connect this, for example. This is a grid line and this is a grid line. Then this will connect here at 1, 1. And then you have 2, 1, 1, 2, and so on. And we are looking at all of these points within this rectangle. Actually, all of the points completely within the rectangle, plus all of the points on this edge of the rectangle, plus all of the points on this edge of the rectangle. And just by direct calculation, you can see that this is actually equal to b minus 1 over, actually, sorry, back here, this is not equal to b minus 1 over 2 plus q minus 1. This is equal to b minus, right? It was supposed to be till 7:30. I think we'll complete it by then. This is actually equal to b minus 1 over 2 into q minus 1 over 2. Sorry. But yeah, I will send the both still. But yeah, so what we need to do is we need to prove that b minus 1 over 2 into q minus 1 over 2 is equal to this value above. That is, let's call this x minus 1 raised to capital X and minus 1 raised to capital Y. This is the theorem of quadratic reciprocity. And what we need to prove is that this is equal to capital X plus capital Y. Right? Where capital X and capital Y are these exponents here. Right? So to prove that, then finally what we do is we count all of the, as I mentioned, all of the lattice points within this rectangle here. So just by direct counting, we can see that that is equal to p minus 1 by 2 into q minus 1 by 2, because there are that many points here and that many points here, and intersection of any point gives a lattice point. Arkan, I'm not really sure. I don't know off the top of it. So this is a rectangular grid, right? Of well, the maximum grid point here is capital P, and maximum grid point here is capital Q, right? And then we divided it into this smaller rectangle at the x-axis value of p minus 1 over 2 and y-axis value of q minus 1 over 2. We are looking at all of the grid points. Yeah, as I mentioned, the theorem is called quadratic reciprocity, as I mentioned. Theorem of quadratic reciprocity. So yeah, we are finally looking at all of the lattice points within this rectangle. Then area I mark here. But we are looking at all of the number of lattice points in this box that I just made, and I think it's, I'm not really sure. Can be law of, no, I think it is quadratic reciprocity theorem. Honestly, don't know what the difference is between naming it a law and a theorem. But yeah, it's just either way, it's a good theorem, so definitely you can use it. Right, so we are looking at the points within this lattice here. No, so this as I mentioned, we have proved, are proving it. So if that is the definition, then it is a theorem. Yeah, this is definitely not an axiom. So yeah, just completing this proof, we are looking at the number of points within this rectangle, which directly from combinatorics comes up to q minus 1 over 2 times q minus 1 over 2. Because for each, well, and that's more of the uh, physics side of things, wherein, you know, at the end of it, everything has to be derived from nature. I don't really think, you know, that holds for mathematics. So in mathematics, at least from till what I have dealt, unless you directly state that it is an axiom, like the five axioms of so again, the basics of it are all, you know, unprovable in a way, because most of the basics of physics comes to right. And again, the number theory just depends on very basic axioms, which just states that there is a number line which behaves as we expect it to. Yeah, exactly. Which just depends on the definition of integers. That's also more of a definition of what a number means, because what define the integers basically depends on is count in a way. So as long as you have defined 2 to be a double of 1, 3 to be triple of 1, and so on, either by addition or by multiplication, then that's all that you basically need to start off with in a way. But yeah, coming back to the proof, we are at the home run. We're just looking at the elements within this, and what we shall, yeah, what we shall prove is that, well, the first thing we shall prove is that this triangle ABM does not really hold any elements other than the elements on AB. So there is no element within the triangle ABM. There is no element on AM. There's no element on MB. Why? Because well, let's just calculate. First of all, let's no. Here we are calculating an exact an equality here. So actually, it's already 7:30. Should we? Does everyone have about 15 minutes more, or should we continue this next class? Shouldn't take more than 15 minutes. Okay, if some of you cannot continue now, then we'll just complete it off in next class, and then continue with the Jacobi symbols. So yeah, let me just download the codes. I'll send you the codes, and we'll continue from this image next class. Thank you, everyone. We'll meet you again next Sunday, I think. Next Sunday. Bye, everyone. Hope you had a nice day. Hope you understood everything. Good night, Vidya.